Okay, so this is Thursday, September 16th, and we're going to call this lesson Rational Exponents Continued. Here's today's first example. So 40 times 48, all to the 1/3 power. So we know what to do with that 1/3 power. We're going to convert that to a radical sign, a third root radical, because it's a 1/3. Before we do that, I want to simplify the 40 and the 48 by using a factor tree. I want to break those down to their smaller components, the factors that multiply to make a 40 or to make a 48. So let's start with that like we've been doing. So side work, I start dividing 40 by anything until I just get whole number answers. Let's start by dividing it by 2. So 2 times 20 makes 40. And continue breaking down that 20 further. So let's say 2 times 10. And then for 10, we get 2 times 5, and we're done. So 40 is equal to all these numbers that I circled at the end of that each like root of the factor tree. So we've got 2 times 2 times 2 times 5. And I'm going to rewrite that as 2 to the 3rd power times 5. Any questions, please, on that process? Concerns? Okay. Then we're going to do the same thing for 48. And then we'll get back to actually simplifying the problem in black that was given at the top. So we could just start by cutting it in half. If you see a bigger number you want to start with, like 4 or 12 or something, go for it. I'm going to start with 2, just because it's something I can count on. So 2 times 24. 24 can still be broken down, divided. So 2 times 12 makes 24. Okay, 2 times 6, and then finally 2 times 3. So 48 is what? 2 times 2 times 2 times 2 times 3. So 4. So you know what? I'm just going to cut straight to the exponent like form of writing it. So this is 4 2's, right? So that's 2 to the 4th power times 3. Okay, now we've done most of the work already. This is going to come in really handy. Let's substitute these expressions for 40 and 48 into the original problem at the top. So 40 is 2 to the 3rd. Here, I'll draw a line here so we know we're working on the actual problem, not the side work. So 2 to the 3rd times 5, that's my 40, times 2 to the 4th times 3. Okay, there's 48. Any questions on that before we continue? Okay. I'm going to go ahead and, since I've got 2 to the 3rd, notice, and then I've got 2 to the 4th, those are the same base, right? So back to day 1, same base, being multiplied together, we can add those exponents. So I'm going to combine those 2 to the 3rd, 2 to the 4th, into one like packet instead of 2 terms like it was above. Okay, now before I keep writing, let's just think about what we're doing here. We're going to multiply that 1/3 power to the inside powers. Don't forget that everything inside the parentheses is getting raised to the 1/3, even the 5 and the 3. So for me, I like to remember, okay, in order to not forget about that 5 and 3, let's give them a 1 power right now, so we don't leave them out of the multiplying that we're about to do. One other thing, folks, it might be good also, because we're going to multiply in a 1/3 power. I know I want like groups of 3 items, right? Now, I've only got 1 5. I've only got 1 3. So we know already that we're not going to get to like simplify any exponents for the 5 or the 3. It's going to be 5 to the 1/3, 3 to the 1/3. So the action is here, 2 to the 7. Let's separate that into like groups of 3 now. Okay, so that way when we multiply it, we'll get some clean reducing when we simplify it. So what I mean by that is this. Let's kind of separate our 2 to the 7th into chunks of 3. So 2 to the 3rd would work, but there's still leftover, right? There's 4 more 2's there. 2 to the 6th would work. And then that would, we can separate out 2 to the 7th like this. 2 to the 6th times 2 to the 1. I'm kind of doing a little bit of work ahead of time, so that way it's cleaner and easier once I multiply my 1/3 in. I'm sure there's probably some questions going from this line to this line about what happened with those 2's. Any questions, concerns? You also might be thinking, well, why did we even make the 2 to the 7th in the first place? And that's a valid question. Maybe I shouldn't have made the 2 to the 7th in the first place. So maybe a better way to approach this would be if back here at step 1, I look at my 2's, 2 to the 3, that's already a group of 3 items. 2 to the 4, that would be 2 to the 3 times 2 to the 1. So maybe I should have separated it out right here for the future. Separate out groups of 3, right? Because I've got a packet of 4 2's. So let's cut 3 of those off to the side and call it 2 to the 3rd, and then times 2, or 2 to the 1. Groups of 3. But anyways, I did that now in my 3rd line. Okay, so now finally I think we're ready. Let's multiply that 1/3 in. So we've got 2 to the 6 over 3, 2 to the 1/3, 5 to the 1/3, times 3 to the 1/3. Okay, and then this one, 6 over 3, the first 2, 6 over 3 is 2 itself, so this is 2 to the 2nd power. And then I've got these 1/3 powers. So what do we have? 2 to the 2nd power is 4. And then these other 3 items that are all to the 1/3 power, they can't be reduced. I can't mix them together, right? Because they're different bases. So I'm going to kind of undo what I just did and put those all into a 3rd root radical box. I'm going to do this in one step. So we've got 2 times 5 times 3. In general, we do use the radical boxes, but we should be able to like hopefully feel comfortable using either, right? As a 1/3 answer or the radical box. And now since I've got this multiplication inside the radical box, let's just finish it off by multiplying those back together for like a number answer, not a multiplication answer. All right, so right on the right side here, we've got our 4 root 3 of 2 times 5, that's 10. 10 times 3, that's 30. So it looks like this whole deal turned into 4 third roots of 30. Questions, concerns, comments?
Did the 3 come from the 1/3? The 3 being on the little like radical piece on that
Correct.
side.
Absolutely. Yes, Aaron, that's exactly where it came from. So yes, that's where it came from. You can think of it like this way. I will say, folks, I did kind of skip a few steps in these last 2 lines right here. You couldn't think of it as like 2 to the 1/3. Well, that's root 3 of 2. And then same for 5 and 3. So each one turns into like their own separate one, like this. And we're going to combine all those together because it's the same root. They're all being multiplied. And that's what I did in those last two steps. I basically converted each one back to third root instead of one third power, and then I combined them into one. And then since it's like, okay, we're done, I can't pull anything out of this third root box because it's just a single 2, a single 5, a single 3. So I'm going to multiply those back together to get a nice clean 30 instead of this multiplication. Okay, there is like, I think, two problems like this on our test coming up for next week, where it starts off the same, 40 times 48 to some fraction exponent. And then our job is going to be to clean it up and show what it looks like once we pull as much out of that radical as possible. So I guess you could say we pulled out the 4, right? This whole number 4 initially would have been inside the radical because it was 40 times 48. Those two numbers together made up the 30 that we see at our answer, and um, 4 to the third power, which was inside there as well. We just cleaned it up in this work, simplified it as we went. Okay, I better move on. Example 2. We've got 3 times just square root of 6 times 10 square root of 8. Okay, so I mentioned this yesterday, and I wanted to do more with it today. And this is the one that's like question 5 that Aaron mentioned for yesterday's homework. So if we're multiplying together two numbers, two terms, this is our first number, and this is our second number. If there was no square roots here at all, so no square root 6, no square root 8, then it would just be 3 times 10, right? So we do multiply the outside numbers, kind of like the coefficients, 3 and 10. Those are going to get multiplied together to make 30 right off the bat. And I'll do this in a few steps. Then we've got root 6 still hanging out times root 8. Now, just like the last example, if you're multiplying together two roots and they're the same root number, like this is a square root and this is a square root, there's no little symbol there, there's no number. So we treat it like it's a 2, right? It's like there's an invisible 2 there. Now I've added the 2. Anyways, they're the same root. So we get to multiply this to this. So next is 30 root 6 times 8, 48. Questions so far? No? Okay. So this almost looks like we're done, except let's check and see if we can clean up that root 48, meaning can I pull out any number from inside there? So to figure it out, what do? We make our factor tree. Side work. 48 is 2 times 24, 2 times 12, 2 times 6, 2 times 3. So 48 is 2 to the 4th power times 3. So back to our problem. I'm just going to substitute what we just found 48 to be equal to. 2 to the 4th times 3. Okay. Now, if we're doing a square root, this is a square root, meaning we're looking for squaring, right? Now, inside here, I've got 4 2's and 1 3. So that 3 we know right now is going to be trapped inside. It doesn't have a buddy to match up with to become a square to get out of the square root box. But the 2's, we know there'll be some simplifying. So to do this the shortcut way from yesterday that I went over with you all, we can just split up our 2 to the 4th into like groups of 2. So what I'm doing is kind of undoing the product rule from last week. 2 to the 2nd times 2 to the 2nd, that's 2 to the 4th. I'm kind of dividing that into 2 little chunks so that way I see groups of 2 items. And then there's times 3. So this first way I'm showing you is without any fraction exponents. Now, because we've got this first 2 to the second power, that's the square root of 2 to the second power. So the squaring and the square rooting cancel out, and we're left with a 2 on the outside. So that one gets to like come outside, so to speak, because the second power and the square root are canceling. Same story for the 2 to the second power next to it. So that gets to come outside of the square root box. The 3 is all alone. It doesn't have a buddy, a square, an extra 3, so it's trapped inside like this. So what's left? 30 times 2 times 2. 120. 120 root 3. And that's it. So really quick, we can also do this problem, or at least see it, visualize it with our fraction exponents. So maybe from this stage right here, I'll try showing you the other way we could think about it. So if we, back here at this line, 30 root 2 to the 4th times 3. So let's say you wanted to try doing this with fraction exponents instead. It's the same problem, and the same things will happen, but they'll just look a little different. So square root, we convert to the 1/2 power. Then let's go ahead and hand out that 1 over 2 to all the inside numbers, their powers. So that would be 30 times 2 to the 4 over 2 times 3 to the 1/2. Now, 2 to the 4 over 2, 4 over 2 is 2 itself, right? So we've got 30 times 2 to the second power times 3 to the 1/2. 2 to the second power is 4. Can't simplify or fix or clean up that 3 to the half, so that's just going to be square root of 3. We've got 4 times 30, that's 120. And there's the same answer, but done with fraction exponents. So I just want you to see it's okay to do it either way. I'm not trying to force you to do it one way or the other, but they're the same principles are at play here. It's kind of a personal preference thing. And I want you to have that knowledge, at least be exposed to both, so that way you can choose. Questions, comments, concerns, please.
So I know you at the end we just multiplied 30 by the twos, but
Yes.
why didn't we just like find the square root like we did 48, or do the factor tree like we did for 48? Is it just easier to just have 30 there? Like
Oh,
the
okay.
30, like why didn't it get
Factor treed.
down? Yeah.
Okay, well, good question. Because the 30 is outside already. Let's see here. Where did the 30 come from? Like looking back through this, it came from the 3 and the 10, kind of from the very beginning, right? So when we start this whole problem, we started by multiplying together 3 times 10. They're on the outside. So think of them as like normal numbers, normal 3, normal 10. But the 6 and the 8 are not normal. They're the square root of 6, square root of 8. So they're kind of trapped inside the boxes until we see if we can take any out. And that whole taking some out, simplifying, is the where we use the factor tree for.
Okay.
So I hope that answers your question. The 30 didn't need it because it was already outside and we're not taking the square root of it. Is that okay?
Yeah.
Okay. Anyone else, please? Okay. Now I think that's it for examples today that have like numbers in them. From now on I want to practice doing the same types of problems but with variables, and it is going to be heavier with the fraction exponents instead of just radicals. So here we go. And you know what? Hang on. Before you write that down, just look at these. I'm wondering if I should have ordered them a little differently. Okay, let's just do it the way I ordered it. Okay, here we go. So example 3. Now this could be a little messy. I made it bigger, hopefully, so you could see it better. I'll write it down next to it just so you see it in another form. So it's x to the 1/2 times y to the negative 1/3 over x to the 1/4 times y to the 1/2. So we've got two variables, two different bases, x and y. We've got all exponents are fractions, rational, and we've got one of them is negative. So quick reminder, negative exponents. We were heavier on this last week, but whenever you see a negative exponent, what does that mean again? Can anyone tell me? Any thoughts on that? A negative exponent.
Don't you move it down
Yes,
or like
Avon,
flip it?
high five. Yep, we move it. We change its position. Since the y to the negative 1/3 is starting up in the numerator, we're going to move it down and then make it y to the positive 1/3. Thanks, Aaron. So let's see. I'm going to draw a line here to show my work. So down below here, underneath that line, we'll do the work. Let's start by moving that negative exponent y. So let's see what we actually have. X to the 1/2 over x to the 1/4 times y to the half times y to the 1/3. So step 1, let's get rid of that negative. I don't like negative exponents. We want to make them positive whenever we can. Okay, now, essentially, folks, we just want to combine the y's together and combine the x's together. Last week, this was easier when they were whole numbers. The same rules apply when they're fractions. Let's see, I'm going to change to red here. There we go. Okay, so I want to focus on one variable at a time, just my x's, okay? So let's just look at the x's, and then we'll kind of come back and look at the y's. So for x's, I've got x to the half over x to the 4th. Now, if you remember back to last week, around this time, we were doing the product rule and the quotient and division rule. The quotient division rule said, same basis, like x and x in this problem. Then to simplify it, we can just look at their exponents and do top exponent minus bottom exponent. So that would be 1/2 minus 1/4. X to the 1/2 minus 1/4, like this. That's what's happening. We're literally just looking at the exponents and still x to the power, but it's the top minus the bottom exponent. So the problem here is we just have to subtract these fractions. So quick reminder, I don't think we've done too much fraction, like actual simplifying in this class together yet. So whenever I want to add or subtract fractions, they have to have the same denominator. So this is a 2 denominator and a 4 denominator. So our job is going to be to force that 2 to become a 4. So I'm going to multiply 1/2 by the number that will make a 2 into a 4. Now it turns out it's 2 itself. So here's how that looks. I'm going to multiply it by 2 over 2 because that'll give me a 4. So that way we have matching denominators. So, question, please.
Just I thought when it was like 1/2 minus 1/4, I thought the 4 and the 2 would multiply to make like 8 in order to get like a common denominator.
Oh, good. So you're not wrong. We could do that. So I think, Leja, if I can jump in again with you, I think what you're saying is do 4 times 4 on the left and then 2 times 2 on the right. Like this. Let me just zoom in on our fractions and forget about the x's for a second. So here's our math problem, and you're saying this, right?
Yeah.
Yeah. And this will work, okay? This will work. The reason I wasn't going to do that above is only just because in this case, Leja and everybody, um,
Mhm.
we can actually kind of make the same common denominator, like you said, but
Mhm.
we could get away with just fixing one fraction and not both. Why? Because I look at my two denominators, 2 and 4, and I ask myself, can I turn a 2 into a 4? Can I multiply it by anything and make it a 4?
Mhm.
Sure, right? We can do 2 times 2 would fix it to a 4. Um, and if we do it this way, multiplying both of them, this will still work. It'll just, I think we'll have an extra step of reducing.
Okay.
So no problem. We can do it both ways. In fact, let's finish it with both ways. So I'm going to finish it with doing both of them here, kind of in the bottom. So this becomes
Mhm.
4 over 8 minus 2 over 8. And now we're just interacting the top numbers, the numerators. So 4 minus 2 is 2. So 2 over 8. And we will reduce this because even, and that's 1 over 4. And coming back up to the top with my x's, if I fix that one up, 2 times 1, that's 2 over 4 minus 1/4. Continuing right below. And we have 2 minus 1 numerators, and that's 1 over 4. So we got 1/4, we got 1/4. So Lasia, I want you to continue doing it that way because the way you said will always work.
Okay. Thank you, Josiah.
Yeah, thanks for asking. Good question. So let's see here. Sorry about I'm running out of space. So let's see. X to the 1/4 is kind of like our answer for x's. So I'm going to go ahead and circle that. And you know what, folks? I'm going to move to a blank screen. So what we're going to do next is we have 1 over the y's, okay? Or I guess we can think of it as x to the 4th over the two y numbers. So let's do that here. Same problem. X to the 1/4, we had y to the half times y to the 1/3. So remember, the product rule says same bases being multiplied together, we can add the exponents. So we want to add 1/2 to 1/3 for my y's, kind of like this. To see it written out. Okay, so it's the same kind of problem as before. And this time we have to do it by multiplying both fractions, just like Leja pointed out for the last problem. So side work, I'm going to just add 1/2 to 1/3. So we're going to multiply a half by 3 over 3 and multiply a third by 2 over 2. We're just looking at each other's denominator and kind of like multiplying the first one by the second one's denominator and the second one by the first one's denominator over itself. It's a mouthful to say. Forgive me. But let's do the multiplication. So 3 over 6 plus 2 over 6, and that is 5 over 6, 5/6. So my y's are y to the 5/6. So what's our final answer here? X to the 4th over y to the 5/6. Okay, they're not the same bases, x and y, so we can't interact them and combine them. So we're done.
So that's the answer?
Answer, yep, you got it. Questions, comments, concerns? This problem, really, most of our work was just adding and subtracting fractions. And remembering our rules, like how do I combine x's on top and x's on bottom? You subtract the top minus bottom exponent. How do I combine the two y's? They're being multiplied. They're the same base, so we add the exponents. Okay, no questions. I'm going to go back to our next question. All right, example 4. Okay, simplify. We've got a to the negative 2 over a to the negative 6, and that's all being raised to the 1/2 power. So there's a lot going on here. Whenever you see a negative exponent, I want you to first think switch places. Then I've also got a over a, right? Same base over itself. So we can interact the top and bottom like terms this time. And then lastly, we've got a 1/2 power. We know what to do with that. It's going to multiply to the inside powers. So why don't we start this mess by doing our negatives, okay? So below here, I'm going to start by moving my positions, changing positions because of those negatives. So here we go. I'm going to keep my parentheses and the 1/2 power the same for now and focus on the inside of the parentheses. So I move my a to the 6th up and my a to the 2 down because of the negatives. And now they're not negative. Now they're positive. Okay. Um, we just did this in example 3. Top exponent minus bottom exponent. So 6 minus 2. What's happening is our answer for this is a to the 6 minus 2 power. Top exponent minus the bottom. And it still has that 1/2 power on the outside waiting for us. And then, so 6 minus 2 is 4. So we've got a to the 4th raised up to the half. What do we do with that outside power, folks? We multiply it to the inside. So we have a to the 4 over 2. You recognize that fraction, that division can work out cleaner. 4 divided by 2 is 2. A to the 2nd power. Is there any more work we can do here? No. This is pretty darn clean. I like it. I want you all to understand the way I just did this. We used our different rules, our different laws, right? We used power to a power by multiplying the half to the 4. We used power divided by a power, the quotient rule, by subtracting 6 minus 2. I guess it's only those two rules. And you know what? We could have done this problem in a different order and it still would give us the same answer. For instance, let's look at the top above my line I drew. So on the top part of the page, let's say we wanted to do the power to a power first. Let me show you what that looks like. So a to the negative 2 over 2, I'm multiplying in my outside power to all my inside powers, even the ones in the denominator. So a to the negative 2 over a to the negative 6 over 2. Now there's no more outside power. So we did that first this time. And now let's simplify those fraction exponents. Let's deal with the negative last. So what's 2 over 2? That's 1. So this is a to the negative 1. And on the bottom, we've got a to the negative 6 over 2. So 6 divided by 2 is 3. A to the negative 3. Now, I guess let's go ahead and move our negatives, change positions. So we have a to the 3 on top, a to the 1 below. And now let's go ahead and do our division rule or quotient rule. So top exponent minus the bottom, 3 minus 1 is a to the 2nd power. Same answer, but a different path to get there. As long as you use all the rules that apply to that problem, we should get the same answer. And if you don't, then that means there was a mistake made somewhere along the way. Just forgot about a rule or forgot about, just made a little mistake. But what I'm trying to drive home here is that you don't have to do it just my way. As long as you are using all the different rules and simplifying it down, you're doing fine. Questions or concerns? Please. No. Okay, let's see. I tried to make today shorter, but we might not get through all my examples still. Let's look at number 5. Oh, that's weird. Darn it, I must have not saved it when I... Okay, so 5 is the same as 4. So go ahead and label this number 6. I didn't do a 5. Example 6. we've got c to the second times d to the seventh over d to the fourth, and it's all being raised to the 1/2 power. So how do we start? Well, like I was saying in the last example, we can do it frankly in any order. We could start by handing out that 1/2 power to all the inside powers. We could start by simplifying the d's together on the inside before we hand out the 1/2. And I'd like to start that way. I'm going to combine together the d's because they're the same base. So let's see what that looks like. We can't really touch any, we can't really change or affect c right now. So that's just c to the second. But d's, top minus bottom exponent. So that's d to the third. 7 minus 4, d to the third. And now I can't combine c and d, different bases, right? So let's just hand out the 1/2. That's all we can do, I think. So c to the 2 over 2, d to the 3 over 2. 2 over 2 is nice. That comes out to just c to the 1 or just plain old c. D to the 3 over 2. That doesn't come out clean, so we're kind of stuck here. D to the 3 over 2. Now, in Admentum, when we do our unit test next week, you'll have some questions that end like this, the fraction exponent. But how would I convert this d to the 3 over 2 for a radical if that's how our answer was given? Anyone want to help me convert d to the 3 over 2 power to the radical form? Because these are both valid answers. Okay, remember, when you have a fraction exponent, and if we need to convert it to a radical, the bottom number, the denominator, the 2, that's our root. And the top number is still a power for the base. So you might see solutions in either way, and we just need to remember we have to be able to convert back and forward between the 3/2 power or the second root of d to the 3. Same thing. Any questions or concerns?
I mean the CD to the 3 over 2.
Yeah.
The answer is still correct, right?
Yes.
But the C to the second root of whatever, that's just the simplified version of it. So we could put both.
I'm not even in. You're right. Correct. I don't know if we should say it's simplified. Honestly, I think they're both just as simplified as the other. It's kind of just like different form. These are both. Here, let me write this down. Thank you. Good. Both good answers or solutions.
Mhm.
Just different forms.
Okay. Thank you.
Sure. Thanks for asking. Sorry I wasn't clear. So we've got our exponent and then we've got radical. So just keep that in mind. Your answers might be with the exponent form or the radical form. All right, let's try example 7, which is also a copy of number 6. Darn it. That means I didn't save it when I was making my other problems because I did make all different problems. Let's look at this one, 8. We have time for at least one more. So copy this down. And even though it looks messy, remember, one step at a time, these are going to whittle down and become smaller, clearer, less messy if we just use our rules. We've got e times f to the third raised to the 1/2 power divided by e times f to the negative 1/2 power. Now, because they're the numerator and the denominator this time, they're kind of each being raised to a different exponent. one is positive a half, and the bottom is negative a half. We can't really jump right into um, combining our e's together and combining our f's together because the exponents are different in this case. So in this case, I am going to start by dealing with the negative one half, or just say negatives, negative exponents. So what do I do with that negative power? I'm going to move that base up, change positions, and then it becomes a positive power. So here we go. I'll write down the whole thing, EF to the third to the one half over EF to the negative a half. So start with that negative a half basically. So that moves it up. It becomes EF to the third to the one half. So that's the same numerator, haven't touched it. And now our denominator changes positions like this. EF to the half. And there's no more fraction. There's no more denominator. So that's nice. Now, we can start by handing out the one half powers. And you know what? Why don't we do that? Let's, everything gets the one half power in both parentheses. So what do we have? We've got e to the half times f to the 3 halves times e to the half times f to the half. Okay, now let's combine our e's and then we'll combine our f's. So just focus on the two e's here. What do we do when we have same bases being multiplied together? What's the shortcut? What's the product rule? What do we do with those exponents? Anyone remember? We can add the two exponents if they're the same base, right? So e to the half times e to the half, that's like saying e to the 1 half plus 1 half. And you know what? Same for the f's. This is f times 3 half, or I'm sorry, f to the 3 halves plus 1 half. I've combined my e's together and my f's together. And we've got to deal with the fractions. Sorry. There we go. All right, so my e's, let's continue. So 1 half plus 1 half, that's just 1. Or 2, I guess I should say it's 2 over 2, right? 2 halves. Let's do that. 2 over 2. And then my f's is 4 over 2. And continuing up, just because I'm out of space, this is e to the 1, or let's just say e. And then 4 over 2 is 2, so f squared. And there's our final answer. Yes.
I'm so sorry for interrupting you.
No.
I don't know if you're writing or not. I'm looking at example 7 screen.
What? Oh my. It says I'm still screen sharing.
Oh, look, there is an example 7.
So is everyone seeing example 7 right now?
I'm seeing 8.
I'm seeing 8.
I'm seeing 8.
Okay. Leja,
No, it's just me.
I'm sorry that this is happening. There must be a lag.
There you go. It's there now.
It's there now. Okay. Sorry about that. If you look up the video later, you'll be able to see this problem if you want to watch just this one.
Okay.
So these problems do look scary at first, for sure. But the ones that you've seen today with me are, frankly, straight from the test with just letters and numbers changed a little bit. These are the same exact problems that we'll be testing on next week. So I want to practice with these today, obviously, and then all Monday, all Tuesday, and then Wednesday we'll take our test. We probably don't have time for another one. Plus, I make another one. Number 9 and homework. All right, so number 9 is here. You know what? I'm going to do it real quick since we're recording anyways. Here's number 9, p to the 6, q to the 3 halves, all to the 1/3 power. I'm going to start by multiplying in those powers. P to the 6 over 3, q to the 3 over 6. 3 times 2 gave me that 6. Simplify. So this is 6 over 3, that's p to the 2. And q, I can't divide 3 over 6, 3 divided by 6, but it does turn into 1/2. And that's cleaner. So here's our answer. We're done. P to the second times q to the half. Another way to write the answer would be p to the second times the square root of q. These are both legitimate answers, just like that other one. Both good answers. Same thing. They just remember the 1/2 power means square root. So that's all I've changed there. All right. And then I've got 6 problems that come from today's work. So take a picture. I know that it's a lot to write down. And please, when you do send this in to me, label it Exponent Homework 3. It'll just help me organize everything. Shouldn't be any trick questions. It's all just like the ones I did with you today. So I hope everyone's doing okay. I didn't stop to see thumbs today, and I should have. So if you haven't turned in Exponent Homework number 2 from yesterday, that video is up. I'm putting in like the description area, like if there's a homework at the end that you need to find. So that hopefully will help you find the right video. Make sure to find like Math 2, because I've also got Math 1s there. And frankly, guys, I haven't figured out how to separate it and make it so you don't even have to see the Math 1 videos. So they're all kind of mixed up. But you can, they should be ordered from like newest video, right? The latest. So if you go on there today, you should see yesterday's video up first. And then once I get today's up, that'll be on top. Once you have this written down or taken a picture of, you can go for the day, for the weekend. I'll see you again Monday at 10.
Have a good day.
Thanks, Braden.
Bye.
Bye, Josiah.
Bye, everybody. Thank you. Have a good day.